Hello everybody. In this video, this is the first part of the Intro to Manifolds series, and for the most part, I will be assuming that if you're watching this, you're familiar with some, background upper level math, for instance, topology, and real analysis for the most part. There are some topics from my source material that I chose to exclude because they were more algebraic in nature, and I didn't want there to be too many prerequisites. But in this video, I just want to give a quick, well, not, it won't be so quick, but I guess compared to maybe a whole semester, just an overview of the topology that we will be needing for this series. So really, if you haven't seen topology before, then this series probably isn't for you, unless you think you can get a good enough grasp just from this video, which I doubt. Not saying about anyone's personal ability, but just saying on the basis of what I'm presenting. If you come across this video, this might be good as sort of this is probably going to be like a 20-minute video, just a recap of topology if you're studying for a topology exam or something like that. But ideally, this is sort of a review for someone who has seen topology. Anyway, so without further ado, we first want to define what a topology is. So if we're given some set X, we can, a topology is simply a collection of subsets of X, which we call open subsets. So elements of this T, which is called the topology on X, are called open sets. And that's just the definition of what an open set is. It's just an element of the topology. And the topology has to satisfy three conditions. So the first condition is that the empty set and the entire set X have to be elements of the topology, which means that the empty set and X are open. Well, they are closed, but we'll get to that later. I got ahead of myself there. The second condition is that if we have some collection of open sets that is indexed by some set A, which may be countable, or this may be infinite. So this is some collection of open sets. Then this implies that the union of all these sets must also be an open set. And finally, the third condition is, well, succinctly, we can just say that the intersection of two open sets must also be open. And you can generalize this via induction to say that the intersection of a finite collection of open sets is open. So the difference between these two conditions is that the union condition generalizes to an infinite case. However, the intersection does not. So there are examples of topological spaces where you can form an infinite collection of open sets that has a non-open intersection. So X together with the topology is called a topological space. So I'm just going to abbreviate that as top space. All right, so now let's give an example of something you've probably seen. So Euclidean space Rn is a very familiar space to all of us, probably. So for example, I'll just analyze R, the real number line, and we can create a topology on R, so let's say this is 0. We don't really need to know where 0 is, but we can create a topology on R by, formally we would call a basis. I'm not going to define really what a basis is, but we can take these open intervals, so basically sets, so the open interval A to B is just the set of elements X such that A is less than X is less than B. So this is an open interval. And the open sets are then defined by essentially any open set is going to have, or we can take these sets and then form unions or intersections of them arbitrarily, or well, finite intersections and arbitrary unions to generate any open set. So this is what we mean by a basis. There's a more technical definition, but we won't really need that. Now, a thing about open sets is that a set is open if for any point I pick, so let's say I have some subset of a space and I want to see if it's open, then if I pick any point in the set, if I can find some open set, so let's say I pick an open set V, which contains this point, and the open set is contained in U. If I can do this for any, this symbol means for any. If I can do this for any point in the set U, then this means that U is open. Formally, this is because we can express U as a union over all of its elements of these sets V, and since all of these are going to be, you can use an argument to show that these two sets are going to be equal. Right. So an example, if we consider the real plane, right, the Euclidean plane, if you consider this this region, right, x squared plus y squared is less than or equal to 1, this is not an open set, because if you pick a point, for instance, the point 1, 0, any open set around that point, or sorry, I guess I should zoom in maybe as much as I can. Any open set around this point will necessarily have to go outside of the set, and this is the definition of a boundary point. And there's a lot of ways to introduce this material, like going through boundary points and limit points and stuff like that. But that's not the way I learned topology, and it doesn't really matter what approach you take because they're all equivalent. So now let's talk about closed sets. So a closed set is simply just a set such that its complement is open. So x minus c is open, right? And really that's all we have to say. And in relation to these two, so we can derive from this, right? X minus the empty set is x, and x minus x is the empty set. So we can derive from this that the empty set and x are both closed because their complements are open. Also, in relation to 2 and 3, we can use something called De Morgan's laws, which basically says that the union of complements is going to equal the intersection of the sets, and vice versa. So, and I'm using very terse notation here, but we can use these rules to say that, okay, if the intersection of closed sets is equal to a union of open sets, then we know that the arbitrary intersection of closed sets is closed. Similarly, if a union of closed sets is equal to an intersection of open sets, then we know that the finite union of closed sets will be closed. Now, if we take any subset of X, right, it may not necessarily be open or closed, right? However, we can relate this set to the topology on X via the two sets A interior, which can be denoted like this, or possibly A with int in the superscript, but this is how I've learned it, and the closure. So this is the interior, and this is the closure. Now, for most purposes, the interior is completely disregarded, mostly because you can relate these easily. The interior is just the closure of the complement, so you really only need one of these operations, and it just happens that closure is the one more oftenly used. So what the closure is the intersection of all closed sets that contain A. So imagine you have some arbitrary space, and you have some set, okay, the set A, and you're looking at all the closed sets that contain A, and you're intersecting them together. So in other words, this A closure is the smallest closed set which contains A. So for instance, if A is closed, that implies that A closure is just equal to A. And you can rephrase this in terms of limit points, and there will be a point at which we will use this approach, but we will talk about that when the time comes. All right, so now we have to talk about continuity, right? When we have functions between two topological spaces, sorry, that looked ugly. Right, so if we have a function between x and y, where x and y are both topological spaces, what does it mean to be continuous? What it means is that if we have an open set in y, so this is open, then the inverse image of v, which is the set of all points in x which are mapped to v, right? F inverse may not be a defined function, but we can still look at this as a set, right? This is a notation which is just a set of x such that f of x is in v. So for instance, if f is not injective, it may be that there are multiple points in x which are mapped to the same point in v, but that doesn't matter. All that matters, so for a continuous function, we just have to have that this inverse image of v is open for any open set v and y. Now this is the general definition of continuity. However, if you take in even just a normal calculus class, you may have seen the epsilon delta formulation of continuity, which says that for any epsilon greater than 0, we can choose, or there is a delta greater than 0, such that if we take points that are between delta, or that are within delta of each other, then their outputs must be within epsilon of each other. And in fact, if you were going for a general topology, right, then this definition would be better. But since our aim is to study manifolds, and we haven't talked about what manifolds are, but manifolds are topological spaces, which they aren't Euclidean, but they are locally Euclidean. So when we talk about continuous functions between two manifolds, we basically look, within the neighborhood of a point in M, right, we can define a Euclidean space. And so we can use, and then within a neighborhood of the output point, right, in N, we can also define Euclidean space. So we can use this Euclidean formulation of the epsilon delta continuity. So if you want to think about it like that, then that's perfect, because we happen to be dealing with manifolds and not general topological spaces. And also it's important to mention that X and Y, two topological spaces, are called homeomorphic if there is a function f from x to y, which is a bijection, which means just in terms of the sets x and y, just means that that x and y are mapped in a unique, like a perfect correspondence, right? Every point in x is uniquely corresponded to some point in y and vice versa. So essentially saying that x and y are the same as sets, and f sort of encodes that information. So if f is a bijection, then we know x and y are the same as sets. And they are the same as topological spaces if both f and the inverse function f inverse are continuous. So in this case, f is called a homeomorphism. All right, so now let's talk about special topological spaces. First is a metric space, which Euclidean space is one, right? So a metric is a function. So a metric is a function which takes in two elements of the set x and outputs some real number, which is the distance. And it satisfies three properties. The first property is that distance is symmetric, right? So it doesn't matter if we do distance from x to y or distance from y to x. It's the same thing. The second property is that the distance from a point to itself is 0, and the distance from a point to a different point, so if x and y are not equal to each other, then their distance is positive, right? So there are no, put these two together, say there are no negative distances. The third condition is known as the triangle inequality, which essentially says that if you travel basically to an intermediate point, then the sum of the distances from x to z and from z to y cannot be less than the distance, just the straight distance from x to y. And so this is sort of intuitively, and this intuitively makes sense, right? And so an example of this is on Euclidean space, right? We have the metric, which is given by the normal distance function, which is a generalization of the Pythagorean theorem. And also a notational note here. You may be appalled by the fact that I'm putting indices as superscripts. So these are not exponents. So x and y here are elements of Rn, which is an n-dimensional space. So each of these elements x and y has n components. So we're denoting the components like this. And so you may, for previous math background, you may be inclined to put an index as a subscript because superscripts are reserved for exponents. But it turns out that essentially the superscript and subscript notation is more important than exponentiation when it comes to essentially differential geometry is the point where this is set apart. Like if you read anything on general relativity or differential geometry, you will see this notation. It is just a fact of life, and you will have to deal with the fact that subscripts no longer always indicate exponents. Here, of course, this 2 is indicating the square exponent, but this does not mean x to the I. This just means the ith component of x. I thought I should mention that. The next type of topological space is the Hausdorff space, or Hausdorff spaces, I guess. And Hausdorff spaces are also known as separated, well, I guess T2 separated spaces, which basically means if you take 2 points in X which are not equal to each other, then there are open sets such that X is contained in U, Y is contained in V, and U and V are disjoint. So, sorry. Right. So, now metric spaces are an easy example of Hausdorff spaces, right? A metric space is always Hausdorff. Because with a metric space, if I have 2 points x and y that aren't equal to each other, then I know they have some positive distance. And so what I can do is simply split that distance in half and create open sets, which are spheres, right, or circles, or whatever you want to call them, depending on your visualization. Right, these 2 open sets, which are essentially just balls of radius d over 2, they don't intersect, they're open, so x and y are said to be separated by the sets u and v. And from here on out, we will assume Hausdorff spaces. Any topological space that we talk about will assume to be Hausdorff. And a fun historical tidbit is that the Hausdorff condition used to be in the original definition of a topology because all the, quote, interesting spaces were Hausdorff. But nowadays, topology is, a topological space is just the general setting in which we can have continuity, and so that's what mathematicians are content with. Hausdorff is sort of a stricter condition, but you still get most of the interesting topology out of it. Anyway, going on, we now have compactness. So a compact space is one in which if you have a collection, U alpha, so a collection of open sets, so these are open, where x is equal to the union of U sub alpha. So if you union all these open sets, you get x, right? So this is called an open cover, right? Then compactness means that we can choose a finite subcover. In other words, we can pick from this collection U sub alpha, which could be infinite, we can pick a finite subcover with x still equaling the union of these sets. If x is metric, is a metric space, there is an equivalent formulation of compactness, which states that any sequence contains a convergent subsequence. And furthermore, if in Rn, so in a Euclidean space, compactness is equivalent to closed and bounded. And I forgot to mention here that in metric spaces where you have distance, you can define what boundedness is, which is essentially a set is bounded, right? So if I have some set A, a set is bounded if for any point in the set, I can choose some positive distance such that all the other points in A are contained in that within that distance. And so this result is known as the Heine-Borel theorem. Finally, there is connectedness, and there is a general notion of connectedness, and there's also something known as path connectedness. And essentially, we don't need the general connectedness. So in terms of logical implications, so path connected will imply normal connectedness, or sorry, I think this is the other way around. Sorry, I don't. But the point is, there is a normal topological definition of connectedness, and but it's not really easy to work with. Path connectedness is much easier to work with. Path connectedness says if we take any 2 points in X, which could be the same, then there is a continuous path, which is a function from the set from 0 to 1. So in this is a subset of the real numbers, so 0 to 1. So this interval here, the closed interval from 0 to 1, mapping into X such that f of 0 equals X and f of 1 equals Y. And so whenever I say connected in this series, I will be meaning path connected. If you want to know the general definition of connectedness, then you can look that up. Now, I think this video is getting a bit long. There were some other sort of special topologies I wanted to mention, namely the subspace, product, and quotient topologies. However, the subspace topology actually we will definitely need, so I'll just explain that here. Basically, if you take a subset of X, your topological space, then you can just define the topology on A to be all the sets A intersect U, where U is an open set in X. Right? So that's a really quick one. And similarly, the product topology is also easy. And I guess I'll just go over these three. If you know what these are, then you could just close the video out now, I guess. The product topology is a topology on the Cartesian product X times Y. So this is the set of points X comma Y, where X is from X and Y is from Y. So this can be topologized. Again, really what we're talking about here is a basis of the sets U times V, where of course U is open in X and V is open in Y. And so by basis, again, we talked about this with Euclidean space, we just mean that from these general open sets, we can form any open set by taking either arbitrary unions or finite intersections. Finally, the quotient space is best explained with an example. So imagine we take the square, which has its 4 corners, 4 sides, and then this interior, right? What we want to do is form a partition of X. So a partition of X is just a collection of disjoint subsets of X. And I had trouble really making this rigorous when I was writing this on paper. But essentially, let's consider the partition where one element is going to be the 4 corners. Okay. Now, so if we remove these corners, right? So let me remove these corners. What you're left with are 4 open sides, right? So these are open sides. And now let's consider the top and bottom. For each pair of sets which are opposite from each other, pair of points which are opposite from each other, that will be an element of our partition P. So there will be a whole class of these elements, right, for each point on this line. Similarly, we do the same for the left and right sides. We have these 2 points. So these elements are just sets which contain 2 points. And of course, you have a whole class of these. And then finally, for each interior point gets its own point in P. So now we can form a partition, we form a topology on P. And the way we do this is we take a map pi, which is called a projection map. Typically projection maps are denoted by the letter pi. Where essentially we take a point in X and we map it to whatever point in P corresponds to it, right? So the 4 corners, right, if we took any of the 4 corners, they would all map to the same point in P, right? Because this point in P, this is one point in P, which represents the 4 corners of the square. Similarly, if we took these 2 points, they would map to the same point. So what we're doing is essentially gluing together X, right? We're saying, okay, these 4 points are now the same, and these 2 points are the same, and these 2 points are the same. We're essentially saying that these 2 edges are the same, and these 2 edges are the same. And so what we can do now is essentially trace along, if we're traveling along X, and we hit this edge here, then we would end up right here if we were traveling in P. So P is essentially this square now, but instead of having a boundary, the square, you can travel through the edges. And if you hit a corner, right, you would just end up whatever direction you were traveling. And so there's a topology on P, which the topology is defined as the subsets of P such that the inverse image of these subsets is open in X. So these are all of the open sets, are just the sets which have open inverse images under this projection map. So this is the quotient topology. And the space we have constructed here from our square is the torus. Right. It is, let me see if I can explain to you why that is. Essentially, the 4 corners here become this one point. And if you imagined you took out that point, then you'd be left with essentially, right, and then you have these two, this circle here, which is glued together. So imagine, how should I draw this? Okay. Essentially what's happening here is that this point right here corresponds to the four corners, and these circles, which are connected, corresponds to the two edges. And this circle, which goes all the way around, corresponds to the other pair of edges. So essentially, you could take a sheet of paper and roll it or fold it such that these two corners match, and then you would have a cylinder, and then you could turn that around, turn that cylinder, and glue the top and bottom of the cylinder together to form the torus. That's essentially what we're doing here with the quotient topology. Yeah, so anyway, this, I didn't really mean to get into it, but then I mentioned it, and then I was like, oh well, I might as well do it. So this video is probably pretty long by now. But it's really just meant to be a review. If you haven't seen topology before, again, feel free to watch the videos. Like, I appreciate it. It helps the channel. I don't know how helpful the videos will be other than a really surface level understanding of manifolds, but you know, it is what it is. You can always come back to it. So anyway, I hope you enjoyed this video, and I hope to see you in the next one.